we're now going to look at other methods that we can use to draw chemical structures. These methods are very commonly used in organic chemistry, and while they have some advantages and some disadvantages, the main advantage that they have is that they save time and they save space. The disadvantage that they have is that they are all less explicit than a Lewis structure. So we have to be careful because they're going to have features that are assumed, and that can sometimes make them confusing and cause us to make unintended errors. If you're having problems working out a given challenge, one of the things you might consider is to at least draw the section that you're working with in a full Lewis structure, because then you'll make sure that you don't miss something that isn't explicitly drawn in the other way of drawing structures. One of the other things I just want to point out is that many of these methods of drawing structures are quite old because there was a time 50, 60, 70 years ago and more where printing materials, it's like printing books and articles, was much more costly and much more difficult because they didn't have computers and desktop publishing and things like that. They instead actually literally used little letters that were on pieces of metal that they would stack on rows to create a page. In that situation, it became very desirable to minimize the number of little letters and symbols that you would have to use to represent a structure. And so what they were looking for was a way to compact those structures. They're still used today, for example, in our textbook, to save space. I generally often use them to save space and to save time, but I do try to take care that they don't hopefully become confusing. All right, so let's take a look at some of these structures. So one of the things about organic chemists that you're going to see is that organic chemists like to take shortcuts because a lot of their chemistry work and everything is quite work intensive. So they're always looking at ways to economize and save time. So this would be kind of a very simple example of that. If we look at the Lewis structure of this carbon-containing compound, we can see that there's only single bonds, there's only carbons and hydrogens in the structure, and any of the carbons that have a bond that's not to another carbon is going to have a bond to hydrogen instead. So when we look at this carbon on the end, for example, we can see it's bonded to one carbon and then there's three other hydrogens. So one of the first things that chemists said was, is it really necessary to draw explicitly these carbon to hydrogen bonds? Couldn't we just list the hydrogens couldn't we just list the hydrogens immediately after the carbon to which they are attached? We would still draw the bonds between carbons. So this Lewis structure becomes this. We have a carbon with three hydrogens, carbon with three hydrogens. That carbon is bonded to another carbon that has two hydrogens, carbon with two hydrogens, which is bonded to a carbon with two hydrogens, which is bonded to a carbon with three hydrogens. Hopefully you can see right away that this saves a lot of space, and actually when you go to write it saves a lot of time. The other thing that's actually useful about this is that this highlights or sort of allows the overall shape of the molecule to stand out more than the Lewis structure would. The Lewis structure has so much detail that you kind of almost lose the overall picture of the molecule, whereas here you can clearly see that this molecule is a chain of four carbons. Now, this is where organic chemistry laziness, shortcutting, starts to kind of get a little bit silly, okay? So, in the previous one we said, well, can't we just ignore, or let's say not ignore, can't we just not write the bonds to the hydrogens, just list them after? So then somebody said, well, we have these bonds shown between the carbons, but we know that the carbon is going to have to be bonded to something. It's probably bonded to the next carbon. So can't we just skip writing those also? This Lewis structure then becomes this. Here are the 3 hydrogens listed after, and then the bond between this carbon and this carbon is not written, it's just assumed to be there. Then there's 2 hydrogens, then a bond to that carbon, and so forth. This we call a fully condensed structure. Now, frankly, I'm not a fan of fully condensed structures. They have their uses. They can, for example, be useful when we're just trying to write, okay, here's a whole complicated thing, and then, there's a chain of 3 carbons here. They won't need to make a big writing with a lot of space. But when we do branches, they become much more complicated. Because what we have to do with branches is we're supposed to put those branches in parentheses to indicate that they're not in the straight line, but instead are branching off. As a consequence, I tend to avoid these, although unfortunately they are used sometimes in our textbook, again, probably to try to save space. So here's an example of what a fully condensed structure would look like if you were writing it with branches. So what we have here is, I'm going to look at the partially condensed so you can see it. We have a CH3, it's connected to a CH2, it's connected to a CH. Then branching off of that carbon of the CH is another CH3. The main chain continues on to a CH3 also. So we could write it like this. CH3, it's connected to CH2, it's connected to CH. There's a branching CH3 off, and then we continue to another CH3. Even worse, in a sense, what we have is a CH3 and a CH3 both attached, kind of branching from this carbon. So sometimes you might even see this written, both of the CH3s in parentheses with a number 2, meaning one CH3 is branching off one way, one CH3 is branching off another way. Again, when you get used to this, it's not so bad, but it actually costs time to try to interpret this structure instead of just looking at this structure and seeing the main point of this structure, which is I have a chain of 4 carbons and there's a methyl branching off, a CH3 branching off of carbon 2. So in general, if I use this, it would only be used for simple molecules with few branches. The third modification we're going to consider for Lewis structures is called in our book the line angle structure. In other books, it's called the bond line structure or just the line structure. I tend to prefer the bond line. Line angle structures are used by advanced organic chemists to save time and to save space. Essentially, what organic chemists said was, if we're going to condense down this structure, really the only important things are the bonds between the central atoms, like carbon. And since we know that in an organic molecule, most of the time, the central atoms will be carbon, what we could do is we could just draw the bonds, the lines for the bonds, and omit the symbols for the hydrogen and the symbols for the carbon. We will, however, write the atomic symbol for any other elements that would be attached on the end of a bond. So if we look, for example, at our chain of 4 carbons, this becomes this structure right here. And in this structure, what we have is a carbon on the end with a bond to a second carbon, a bond to a third carbon, a bond to a fourth carbon. Since these are all carbons, we're going to just leave them blank, not write atomic symbols, and we are going to assume that unless there is a charge or a lone pair on the blank carbon atoms, those carbon atoms are completely filled with enough hydrogens to give the carbon 4 bonds, which is its normal desired number. So if we look at this end point, which then should represent a carbon, because there's only one line to that end point, we would need 3 more bonds. In other words, 3 more hydrogens to fill that up. So that would be a CH3. In contrast, this carbon already has 2 bonds, so therefore it would have 2 hydrogens to fill it up. Now, if we look at a molecule that has something other than carbon atoms in it, what we're going to need to do is write the atomic symbol for that different element. So for example, this molecule, which has a CH3, a CH2, a CH2, and then an OH, we could write in this way in the bond line structure. We would start here with a CH3, a CH2, a CH2, and then there would be a bond to an OH. And in this case, I condensed the oxygen to hydrogen bond, omitting the line but writing the elements. Now, it's very important to understand that when there is an element, an atomic symbol written at the end of a line, there is not also a carbon. So specifically right here, there is no carbon. There is the oxygen. That's why it's written. In contrast to right here, which is the other end of that line, there's no symbol written, so therefore that is a carbon. These types of structures are really useful because what they do is they focus our attention on the shape of the carbon skeleton, and they also help us really quickly look at the important parts of a carbon molecule, because the unimportant parts are just going to be a whole bunch of lines. They're also extremely useful for drawing compounds, structures that have rings in them, because these structures, when they have rings, they can become very large, and of course we do want to sort of have that ring shape stand out. So this is an example of benzene, which is a molecule that we talked about when we looked at functional groups, written with a bond line structure. If we were to look at any of the carbons of benzene, we would see that this carbon, for example, has 3 bonds to it, so it would have 1 hydrogen, which is not explicitly written. The other thing I would like to point out about bond line structures is that we are allowed to write the hydrogens. It's just that it's not normally done if we're just wanting to put a structure out. But it can be very useful to start writing in hydrogens and other things if we are trying to push electrons, make resonance structures, so that we don't make mistakes and accidentally put unintentionally too many bonds to a carbon that really was already filled with hydrogens. In organic chemistry, it's going to be very important that we begin to represent molecules with their proper 3-dimensional shape. Now, sometimes this is very easy to do. For example, molecules that are essentially linear or planar, we can just draw by aligning the atoms with correct angles in the plane of the paper. So for example, a carbon-carbon triple bond, because the carbons already have 3 bonds on one side, they only have room for 1 bond on the other. And the 3 bonds of the triple bond act like one group of electrons, so they're going to repel this bond on the other. In this case, a bond to hydrogen, they're going to repel that 180 degrees away, which is going to make this linear. Well, 180 degrees in a line, we can just draw all of those atoms in a line on the paper, and that would be a pretty accurate 3-dimensional representation. Similarly, trigonal planar shapes and geometries, because they are planar, we just draw all of the atoms in the plane with a 120 degree angle between them, and that's a pretty accurate representation. The problem becomes when we want to represent tetrahedral shapes. Tetrahedral shapes are harder to represent because there is no way to align all of the atoms in the same plane while maintaining the tetrahedral arrangement. So what we will do is we will try to put as many of the atoms in the plane as we can, and then we'll have to use some other way of representing the atoms that are not in the plane. So if we were to build a model of a tetrahedron, what we would see is we could align the central atom and two of the other atoms attached in the plane. So these three atoms, for example, are in the plane, and they make a V shape, and the bond angle of the V should be 109.5 degrees. The other two atoms then, if we were looking at them from this orientation, they would be pointing in with the V in the opposite direction and the V perpendicular to the plane of the paper, which would put one of the atoms on a bond that would be sticking out of the plane of the paper in front of the paper, and the other bond would actually be sticking back behind the plane of the paper. The other thing it's important to note is that technically from this angle, these two atoms should actually be perfectly aligned and essentially be overlapped on top of each other. We generally don't do that because if we want to write the groups that are at the ends of those bonds, or the atoms that are at the end of those bonds, if we write them right on top of each other, becomes almost unintelligible. So what we do is we just put a little imaginary, very slight imaginary twist into that V so that the two atoms are offset a little bit and we could see both atoms. The twist is arbitrary. We could twist it one direction or the other direction and still be indicating the same atom in front and in back. To indicate then that we are trying to draw an atom, a bond and an atom that's sticking out of the plane like this, what we're going to do is we're going to use what we call a wedge. So the wedge bond starts small on the central atom and it gets bigger as it comes out to the attached atom or attached group. This is kind of intended to show sort of perspective, where objects that are farther away are smaller, and as they get closer to you, they get bigger. So the bond, that end is farther away, it's smaller, and this end is bigger then. Okay? So wedges are used to represent bonds that stick out of the plane toward us. Bonds that are behind the plane technically are hidden, and it kind of has been the case that when people draw three-dimensional drawings, they want to show something hidden, they use dashes. So we use a dashed bond to show that that bond is sticking back away behind the plane of the paper, kind of hidden from us. Now it's important to notice then that what we do is that the two bonds that are in the plane form a V that opens in one direction. The two bonds that are out of the plane, one in front, one in back, form a V that opens in the opposite direction. This is the proper arrangement in order to actually represent a tetrahedron. And we really need to try to maintain these approximate angles. This would be another example of a bond line structure where you can see that we've put the atoms of the main chain into the plane, and notice the V, which is opening downward. And then attached on this second atom, we have another pair of groups, an OH and a hydrogen. And they're arranged so that the OH is sticking out toward us and the hydrogen is sticking back away from us. So the OH out toward us is on a wedge, the hydrogen sticking back away from us is on a dash. One of the big problems that we have when starting to learn how to draw these things is it will be tempting not to maintain this V in one direction, V in the other direction orientation. Specifically, very often people will draw the V in the plane, and then they will draw one of the wedge or dash bonds down into the center of that V like that, and the other one sticking up. This is a completely improper drawing. it doesn't well represent the actual three-dimensional arrangement of the groups around the central carbon. And in fact, if we were to do this in a later chapter, where we're going to look at the specific way these groups are arranged, we would get exactly the wrong answer for that. So it's very important that we don't do this. We don't draw groups down into the planes of the V in the plane. Instead, we make sure that the wedge and dash groups are outside of that V on the other direction.